Assalamu alaikum. This is Shakil Ahmed. Welcome to my tutorial series on statistical data analysis in R. In today's lecture, we will learn about regression analysis in R. When we talk about regression analysis, we have two types of regression we can run. One is linear regression and the other is non-linear regression. In this lecture, we restrict our discussion to linear regression. When the response variable is qualitative, we uh, don't opt for linear regression. When the response variable is numeric, then we opt for linear regression. So, what is linear regression? Basically, when we have a response variable in numeric form and there is a linear relationship between the uh, independent variable and the dependent variable, we just run a linear regression. So I assume that you will know about a linear regression model, but I will just repeat the steps we uh, need to look while applying a linear regression model. First, we need to specify the model, uh, which variables to be included and which variables to be excluded from the model. We just specify the dependent variable and the independent variables in our model. The next step is to look for the data and if the data need to be recorded, then we should look for that and look for any missing values in the data. So this step is basically the data cleaning, where we properly record our variables which we are going to use in model, and clean any outlier or any uh, unusual value in data from the model before uh, running the model in R. So you can do this step in R as well, or in Excel, or in any other software. But I recommend you to do this work in R as well. As in my previous slide, I already discussed how to record and how to construct dummy variables as the regressor. So, and the next step is to do the analysis in R and the interpretation. Our main focus is in doing the analysis and the interpretation in this video, and we can also see the model performance through different model performance criteria like R square value and sum of square of residuals and other uh, uh, model performance criterion like adjusted R square and so on. And then we can compare the different competing models. When we include different set of independent variables in our models, then we have a lot of models comprising different sets of independent variables, so we can compare the performance of different models and retain the model which have the best performance. And finally, we need to report the data. Basically, the summary of the model is usually presented in your final report. So, simple linear regression has some basic uh, uh, assumptions. Basically, when we talk about linear regression, then there are two types of linear regression. One is simple and the other is multiple linear regression. Simple linear regression means that we have only one regressor, and the multiple linear regression means that we have many correlated variables, and we assume that there is no high relationship between the variables included in the model. And the first assumption of linear regression is linearity. Linearity mostly refers to the that the model is linear in parameters, not in variables. We should have uh, parameters linearly related to the dependent variable y, and the error term should have zero mean and the zero variance, sorry, constant variance. Basically, this is also known as the homoscedasticity assumption. For all observations, we assume that the all observations uh, have a common variance and their mean is zero, and there is no autocorrelation, means the error terms don't depend its previous lag value. And uh, in case of any time series data or spatial data, this assumption always fails, and we will move toward other techniques like ARIMA and other spatial models. And there should be no high multicollinearity between the variables. And we also assume that there is no relationship between the regressors included in model and the random error term. So these are all the basic things we need to observe while running and while reporting our model. So we just go to the R and just open our uh, codes like we have a regression analysis. So first of all, we just import the data. Uh, in previous slides, in previous videos we use the heart failure data. So we again import that data set here, which is in CSV format. So these are the variables you can see. We have different variables, and if we want to see the correlation between the variables, just give the command of correlation cor and then data. You will see the relationship between the variables. And if we want to regress the creatinine phosphokinase on the serum sodium, then we just can see the relationship using a scatter plot, using just a plot command like this. Here we can see a relationship between creatinine phosphokinase and this serum sodium. And you can also look for the distribution of creatinine phosphokinase, which is our steady variable, the dependent variable. It has skewed distribution. So basically, the distribution of y and uh, consequently the distribution of error term should be normal. It is somehow positively skewed, but still we can try for a linear regression model. Uh, However, in practical cases, you should transform the variable or uh, apply some other techniques, robust techniques, as the error term don't follow the normal distribution properly. So we just run a model, linear model, lm command, and this is our steady variable, and this is the regression command, and this is serum sodium, which is our independent variable, and the data is dat, which we have already imported. So just run this command. We have uh, the model result. Just see the summary and model 1. We have the summary statistics of the residuals. Residuals has minimum value this and the maximum value this, and the Q1 and Q3 and median. 5 number summary statistics for residual, and these are the coefficients. There are uh, two values. One is the intercept and the second is the regressor which we included in model. This is basically the alpha hat and this is the beta hat. Usually we denote by alpha and beta in standard notation, and these are the standard error of alpha and beta, and these are the t values corresponding to the coefficients, and these are the p values. The p values uh, show that the two coefficients are insignificant as the p-values are greater than 0.05 or zero point 0.01, and at any level of significance the two coefficients are insignificant. So just see the residual standard error, which is sigma hat, and the degree of freedom, which is n minus k, yeah, or n minus 1 in this case, and the multiple r square. This is the r square value which is very low, and this is the adjusted r square value which is also low. So this model is totally uh, meaningless, and we can't interpret on the basis of this model, as the coefficients are insignificant and the r value, r square value is very low. And if we uh, run in ANOVA for this model, the F value is also very low, which also depicts that the model is insignificant as the residuals are higher and the explained variation is very low in this model. So we run another model, which is a multiple linear regression model, where we included three regressors: serum sodium, and the sex of the respondent, and the smoking behavior, and the time. So just run this model, and you can print the model to see a quick view on the model. These are the coefficients, this is the intercept, and these are the coefficients corresponding to the three variables. And we again run the summary of the model to see the detail about the model. These are the summary statistics of residual, and these are the estimates corresponding to different variables, and these are the standard errors corresponding to the coefficients, and these are the t values corresponding to the four coefficients, and these are the p values which also indicate that there is all the coefficients are insignificant in this model. So this model is also not applicable and meaningless, as all the regressors are insignificant. Show me that the serum sodium, the gender of the respondent, and the smoking and time are uh, have no impact, or no uh, significant don't have significant effect on the creatinine phosphokinase. And these are the residual errors, and residual error and the degree of freedom, and this is the r square value which is also too low, and this is the adjusted r square value which is showing negative, which is an alarming sign, as the r square adjusted r square value is minus. So uh, this model is totally meaningless, and we can't rely on such model when we have such type of result. But here we just want to see how we can run a regression model in R. So you might understand the results and how you can run this model. And now if you want to see the model on a test data, basically we want to predict the values for some uh, new data set. So how we can do this, just see here. We can uh, split the data into test and training part with value 0. This is our training data, and uh, the value 1 represents for the cases which we keep for test data. So just create a new variable split and include it in your data set. So you can just run, and you will see a new variable in your data set. If you just run your data head data, just this command, you will see a new variable in your data set, the split, and here the value 0 representing the training data and 1 representing the test data. On the basis of the split value, we can specify, we can separate the data into two subsets. One is the test data and the second is the training data. And you can predict your model too on the basis of test data, just like this. You will see the predicted value for the test data for different values of regressors. We basically, these are the predicted values of the creatinine phosphokinase, and you can just plot this predicted value here. uh, in a plot. Here you have a scatter plot between x and y, where x is the uh, serum sodium and y is the creatinine phosphokinase, and the plot dots color are blue, and you give you can see the title as a regression line, and we add a AB line for model 1, as we have only one regressor. For this case, uh, you will see the predicted values on the line, and these are the actual values. So these this was a short lecture on linear regression. There are many issues with linear regression, but we cannot discuss those issues in detail here. But if you have any query related to linear regression, like the problem of autocorrelation and the problem of multicollinearity, or the problem of exogeneity and endogeneity, you can just write a comment in comment section. I will try to help you in this regard. So thank you for watching the video, and uh, I hope you will learn by practicing these command on with your own data on your own PCs. Thank you.